The timber processing at Holtzsworth using link technology follows a highly automated and optimized flow designed to achieve the highest yield from every log. The core of this system is the Link PRO Max profiling line, which specializes in value-optimized processing of large volumes of roundwood through active curve-following technology. The process begins with the infeed of round logs into the profiling line. Logs ranging from 12 to 60 centimeters in diameter and from 3.00 to 5.20 meters in length are transported to the scanning station. At this stage, a 3D measurement system scans the entire surface of each log. The scanner creates an accurate geometric profile, capturing irregularities, bends, and tapering. The collected data is processed by Link proprietary optimization software, which calculates the most value-efficient cutting pattern for each individual log. This optimization includes the best possible sideboards, center cants, and other products to be extracted. Once the optimal cutting solution is determined, the log is passed to the automatic turning device, which rotates it to the ideal position for sawing. This rotation is extremely precise, with a standard deviation of only plus or minus 6 degrees, ensuring the log is aligned exactly to the calculated cutting angle. Accurate positioning is essential for the profiler to follow the optimized pattern and maximize usable wood. The next stage is the pre-planing unit, or Vorschnitt spanner group. This unit begins to shape the log by removing the outer layer, converting the irregular round form into a more controlled shape. This planning step reduces the mechanical handling effort because the log can be processed regardless of whether it is oriented from the butt or top end. Additionally, the chips and sawdust produced during planing are collected as high-quality material for use in pellet and particle board production. Following planing, the log enters the heart of the system, the profiling and sawing section. The Link Pro Max utilizes an active curve-following sawing method, meaning it does not cut in straight lines, but instead adapts to the natural curvature or spline of the log. This allows it to follow the grain and maximize the yield from crooked or curved logs, something traditional systems cannot do efficiently. The sawing is performed using a twin-shaft saw system, where two circular saws operate simultaneously on separate axes. This double arbor principle reduces the curve, as cutting forces are distributed between both blades. It also results in cleaner cuts, higher precision, and reduced material loss. The final tilt and sideboards are produced with high dimensional accuracy and minimal waste. This process ensures that each part of the log is processed according to its value and shape, resulting in optimal yield with minimal impact on the environment. Once the boards are sawn, they go to the final line, where the boards are sorted and stacked, with workers using forklifts to transport the stacked blocks to the warehouse. At the end of the line, the processed cant timber and sideboards are discharged, optimized for further drying or finishing. The system ensures not only maximum yield, but also high-quality output by adapting to each log's natural shape, minimizing waste, and efficiently utilizing byproducts. The manufacturing process of high-quality dining tables and chairs begins with the creation of a sample. Artisans start by selecting premium materials, primarily solid Canaletto walnut, prized for its rich grain and durability. Designers and craftsmen collaborate to translate conceptual sketches into tangible prototypes. Using advanced CAD software, They create detailed blueprints specifying dimensions, joinery techniques, and aesthetic details. A prototype is then handcrafted, with woodworkers shaping the Canaletto walnut into the base components of dining tables, the sculptural legs. For chairs, the focus is on ergonomic frames, ensuring comfort alongside elegance. Each sample undergoes rigorous evaluation to confirm structural integrity, aesthetic appeal, and functionality. Craftsmen test the joinery, ensuring dovetails, mortise and tenon joints or other connections are seamless and robust. If adjustments are needed, the design is refined, and a new sample is crafted until it meets the exacting standards required for production. This iterative process guarantees that every piece, whether a dining table with a Canaletto walnut base, reflects precision and artistry before moving to full-scale manufacturing. Once the sample is approved, the production process shifts to material preparation and woodworking. Logs of Canaletto walnut are carefully inspected for quality, ensuring only the finest pieces, free from knots or imperfections, are selected. The wood is cut into planks using precision saws, with each piece measured to exact specifications. For dining tables, the solid walnut is shaped into robust, elegant bases, often featuring curved or angular designs that highlight the wood's natural beauty. Chair frames are similarly crafted, with components like armrests, backrests, and legs meticulously carved to ensure consistency. Advanced CNC machines assist in cutting complex shapes, but much of the work relies on skilled artisans who hand-shape and refine the wood. Sanding is a crucial step, where surfaces are smoothed to a fine texture using progressively finer grits of sandpaper. This prepares the wood for finishing, ensuring a flawless base for subsequent treatments. Every piece is inspected to confirm uniformity, as even minor imperfections could compromise the final product's quality. Polishing is the next critical phase, transforming raw wood into a refined masterpiece. The Canaletto walnut components are first treated with a sealant to protect the wood and enhance its grain. Artisans apply the sealant evenly, using brushes or sprayers to ensure full coverage. Once dried, the surfaces are lightly sanded again to remove any raised grain, creating a smooth canvas for polishing. Polishing involves applying multiple layers of high-quality lacquer or wax, depending on the desired finish. For dining tables, a glossy or satin lacquer is often chosen to accentuate the walnut's warm tones and intricate grain patterns. Craftsmen use buffing machines equipped with soft pads to apply the polish, working in circular motions to achieve a uniform, mirror-like finish. For chairs, especially those with exposed wooden frames, the polishing process is equally meticulous, ensuring armrests and legs gleam with a refined sheen. Each layer of polish is allowed to cure fully before the next is applied, a process that can take several days to achieve the desired depth and durability. The result is a surface that not only enhances the wood's natural beauty, but also protects it from wear and environmental damage. For chairs, the covering process is integral, particularly when incorporating saddle leather, a material valued for its durability and luxurious texture. Artisans begin by cutting precise patterns from high-quality saddle leather, ensuring minimal waste and perfect alignment with the chair's frame. The leather is inspected for consistency in color and texture, as any flaws would detract from the final appearance. Using specialized sewing machines, craftsmen stitch the leather panels with precision, often incorporating tone-on-tone stitching for a seamless look. The leather is then carefully stretched over the chair's padded components, such as seat cushions or backrests, which are typically filled with shaped polyurethane foam for comfort. For dining tables with leather accents, such as inlaid panels or edge details, the process is similar, with leather adhered to specific sections using strong adhesives. Artisans use hand tools to press the leather firmly, ensuring no wrinkles or air bubbles remain. The saddle leather is secured with meticulous care, often requiring multiple fittings to achieve a snug, tailored fit that enhances both aesthetics and functionality. The final stage is packing, a process designed to protect the finished furniture during transportation. Each dining table and chair is carefully inspected to ensure it meets quality standards, with craftsmen checking for any imperfections in the wood, polish, or leather. Protective materials, foam padding, and bubble wrap are used to wrap each piece, safeguarding polished surfaces and leather coverings from scratches or dents. For dining tables, the solid Canaletto walnut bases are often disassembled into manageable components to facilitate shipping. These parts are individually wrapped and placed in sturdy wooden crates or reinforced cardboard boxes, designed to withstand the rigors of transit. Chairs are similarly packed, with legs and frames cushioned to prevent movement. Each package is labeled with detailed handling instructions to ensure proper care during shipping. For international deliveries, additional protective measures, such as moisture-resistant wraps, are employed to guard against environmental factors. The furniture is then loaded onto pallets, secured with straps, and dispatched to retailers or customers, ensuring the pieces arrive in pristine condition, ready to enhance any dining space with their elegance and craftsmanship. Since 1947, Casey Industrial has supported forest product manufacturers. Casey Industrial was Uniboard's prime contractor for the installation of a medium-density fiberboard (MDF) production line at their existing facility. Wood chips are delivered by truck and unloaded using tilt trucks. They are conveyed to outdoor storage, then reclaimed and sent through a screening process where oversized chips are reprocessed and undersized ones are used as fuel. Acceptable chips pass under magnets to remove metals, then move to the refining section where they are ground into fibers, dried, and mixed with resin. The fibers are formed into a continuous mat and pressed between heated steel belts to the desired thickness. After pressing, the boards are cooled, sanded to final thickness, cut to size, bundled, and shipped. Waste fiber is recycled or burned for energy, and unsatisfactory boards are reprocessed. The plant integrates environmental safeguards, like exhaust scrubbers and advanced water treatment, to ensure emission control and zero liquid discharge. The construction of a 22-foot center console boat using the cold-molded technique is a meticulous process that combines traditional craftsmanship with modern materials to create a lightweight, strong, and durable vessel. This method involves layering thin wooden veneers, bonded with epoxy resin to form a robust hull. The process begins with constructing the framework to define the boat's shape. A sturdy jig built, typically from wood, to serve as the foundation for the hull. Longitudinal stringers, which run the length of the hull, and transverse frames, which provide cross-sectional support, are crafted from high-quality marine-grade lumber, such as mahogany or fir. These components are carefully measured, cut, and assembled, often using precise templates or computer-aided designs to ensure symmetry and structural integrity. The framework is securely fastened to the jig, forming a rigid skeleton that dictates the boat's final form. Next, the cold molding process layers thin wooden veneers, typically 1/8 inch thick plywood or cedar strips, over the framework. Each veneer layer is applied at a 45-degree angle to the previous one, creating a diagonal, cross-grain pattern that maximizes strength and minimizes flex. High-strength epoxy resin is spread evenly between layers, acting as both adhesive and sealant. The veneers are carefully fitted, often requiring trimming to match the hull's curves. To ensure a tight bond, builders use clamps, staples, or vacuum bagging, which applies uniform pressure to eliminate air pockets and ensure full epoxy contact. This process is repeated for 3 to 5 layers, depending on the desired hull thickness, with each layer allowed to cure fully, typically 24 hours before the next is applied. The result is a lightweight, monolithic hull that is exceptionally strong. Once the epoxy has cured, the hull is removed from the jig, revealing a smooth but raw wooden structure. The surface is sanded meticulously to remove imperfections and prepare for reinforcement. Fiberglass cloth, often in multiple weights for different areas, is laid over the hull's exterior and interior. Epoxy resin is applied to saturate the cloth, creating a waterproof, impact-resistant layer. High-stress areas, such as the keel, bow, and transom, may receive additional fiberglass layers for extra durability. The resin is rolled or brushed on to avoid air bubbles, and after curing, the surface is sanded again to achieve a smooth, professional finish. The final stage involves outfitting the boat with functional and aesthetic components. The center console, housing the helm, navigation equipment, and controls, is installed with careful attention to ergonomics and accessibility. Storage compartments, seating, and deck fittings such as rod holders or cleats are added, with marine-grade materials ensuring corrosion resistance. Electrical systems, including wiring for lights and instrumentation, are integrated into the console. Railings and other hardware are securely mounted, and the hull is coated with marine-grade sealants or paint to protect against UV rays, salt water, and abrasion. The limestone and marble blocks are quarried from Marfilpe's quarries in Portugal and Angola. The process begins with controlled drilling and wire sawing to separate the large blocks. Excavators and loaders are used to separate the blocks. The blocks are then transported to the factory where they undergo preliminary cutting using bandsaws and block cutters. After trimming, the slabs are reinforced, dried, and polished to the desired finish. Advanced CNC machinery is used to shape and finish the custom products. Once the slabs are finished, workers stack the slabs together, and load them onto trucks for distribution. Throughout the process, strict quality control procedures ensure consistency. The mobile crushing and screening process begins with material fed into a powerful hydrogen phosphide and GP 220 cone crusher. Crushed material is then transported via a centrifugal lifting conveyor to a 5x18 triple-deck screen, which separates it into 3 calibrated end products. The entire unit, compact and easily transportable, is quickly set up using hydraulics. Operation, process optimization, and real-time monitoring are managed through the IC600 and IC800 intelligent control system. When combined with the LT106 unit, both machines interlock via a cable, functioning as a single synchronized process line powered by one Cat C13 engine. The rock splitting process begins by drilling several holes into the rock surface along the intended breaking line. Each hole is carefully aligned and spaced to ensure an efficient fracture. Next, the super wedge system is inserted into each hole. This system consists of a central wedge and 2 counter wedges. A hydraulic splitter then drives the central wedge forward, pushing the counter wedges outward against the inner walls of the drilled hole. This action generates an immense and focused force that splits the rock precisely along the planned path. The process is repeated across all drilled holes to gradually fracture and separate large sections of rock. This non-explosive method minimizes vibration, noise, and flying debris, making it ideal for use in urban or sensitive environments. The resulting rock fragments are then removed using heavy machinery, allowing further progress in the road construction project. A concrete layer is first placed to provide a level working surface. The base, weighing 9.5 tons, is delivered on pallets and installed within a day. Once the plinth is leveled and aligned, both a large and a small crane are attached to the tower section. The large crane lifts the segment while the small crane helps guide it under the main lift. The section is lowered gently onto the foundation bolts, which are then tightened to 2,000 Newton meters. Technicians climb to release the lifting equipment. This process is repeated for the remaining 3 tower segments. Next, the hub is lifted into position, reaching 85 meters in height, which takes about 10 minutes. Blade installation follows. Bolts are inserted into the blade on the ground. Once prepped, the banksman signals both crane operators to lift. The banksman ensures the blade stays level. Once visible from the top, the banksman guides the blade into final position and secures the nuts. The main crane is released, and the assist crane tilts the blade's tip using a rope to release the sling. The crane is then moved away. After clearing both cranes, the rotor is rotated for the next blade. The process is repeated for the second and third blades. Once complete, the turbine is ready for operation. In September 2011, the Duero Basin Authority initiated the project to demolish the Logera Dam on the Bernesga River in Leon, Spain, to restore the continuity of the channel. The demolition began with the construction of an access ramp using sediment from a former river basin and concrete debris from other restoration activities, respecting the existing riparian vegetation to stabilize the material and minimize environmental impacts. The demolition began in the gate area, removing all mechanical components and renovating the gate mechanisms. At the same time, the Fisheries Department of the Castilla and Leon regional government used electrofishing equipment to rescue aquatic fauna, requiring repeated sweeps due to the high fish population. An opening in the back of the ring channel allowed for a controlled reduction of the water level, which initiated the mobilization of sediment near the dam wall, mainly gravel and decimeter-sized blocks. The main demolition phase involved reinforcing the channel area with concrete blocks to allow machinery access to the wall. The heavily reinforced gates were gradually dismantled by excavators and backhoes, separating the metal from the concrete to selectively remove debris. The backhoe cleared the mud from the dam head. A 1-meter deep hole in the center of the dam lowered the water level further, exposing 90 years of accumulated sediment. The receding water formed the initial rapids, with deeper areas near the dam wall requiring debris to ensure machinery could pass. The dam wall, consisting of stone blocks held in place by unreinforced concrete, was carefully dismantled, with blocks placed on the upper dam section to minimize material falling into the lake. After 2 days, the water level had completely dropped, and all remaining sections, including the concrete foundation, were removed. The natural river had mobilized a large amount of sediment, especially boulders, downstream. Over the following months, the Bernesga River regained its original flow, with ongoing monitoring to study natural regeneration processes. The installation process begins with the rail lifter raising the rails slightly to allow sleepers to be placed underneath without disturbing the ballast. Sleepers are automatically fed forward from the transport wagon by a loader. As each sleeper reaches the end of the conveyor, it is accurately positioned onto the ballast bed beneath the lifted rails. A fastening unit immediately secures the sleeper to the rail using fast clip FC or FE components in the same motion, ensuring stability and alignment. The process continues sequentially, with sleepers laid at consistent intervals. Laser-based distance measurement can be used to control the spacing precisely, maintaining uniform track geometry. Sleepers are ideally delivered in stacks of 6 to streamline feeding and reduce downtime. Only a machine operator and minimal ground personnel are required, making the process efficient and safe while minimizing interference with the prepared track bed.